from Pierre and Marie Curie University Jussieu in France. Okay, and today he lectures on multigraded Sylvester forms, duality and elimination. So, Marc, please, we are waiting for your nice talk. Thank you.
Thank you, Jürgen. Oops, I'll try to present. Hopefully it will work. Is it working? Yeah, it's coming? Yeah. Okay.
Okay, perfect.
Good. Okay, so thank you very much, Jürgen. In fact, my university changed name. Now it's Sorbonne University, but it doesn't matter. Okay, so so this is joint work with Laurent Buzet and David Nemati. And now I have to see how to change slides like this. No. Why do I change my slide? Okay, maybe like this. No. Like this. No. Well, I have to find out. Maybe I should go on the thing itself. Okay, yeah. Okay, and oops. I should find how to present here. Okay, no, this does not work. Presentation. Maybe like this. Yes, maybe. Okay. Yeah. Yeah. So I wanted to start with where I just learned. I just learned at the beginning of the week that our colleague and friend Romer Vasconcelos passed away, and I wanted just to say a few words about him. He was really a beautiful person, a beautiful mathematician, a beautiful mind, and also show a picture of him with Kunz, who also passed away this spring. And these were two fabulous people. Okay, now let's move to the talk itself. And whoops, I should switch between things. Is this okay? Well, anyway, I will do like this. So I will lecture on this work that is mainly about elimination. And I wanted also to mention one colleague who did a lot of work on that. And in fact, I learned a lot from him on this subject. And he somehow set up the modern theory of elimination. It's Jean-Pierre Joannolou. And so many results I will quote as like the background in this talk are due to him. And so that's it. Okay, and so let me start now. So I will start by explaining what is the situation and what is known and what we do in the usual case. The usual case corresponds to a projective scheme or homogeneous polynomial. So this are I will take the standard grading in this talk. So you take n+1 homogeneous polynomials in n variables. One can do with less and with more, but that's the standard case, and I will stick to the standard case. So n+1 homogeneous polynomials in n+1 variables, and you give some degrees, d1, dn. And for most of what I will say, you can work over any commutative ring, K. And now you consider these generic polynomials. So the coefficients are themselves variables. Okay. And so let's set the notation. So this exponent will be a multi-index, and x alpha will stand for the monomial x0 to the alpha 0, xn to the alpha n, and the value of alpha will be just the sum of the alpha i's, the usual notation. And then you consider the universal ring of coefficient, where you add to your base ring k. You can think it's a field, but it doesn't matter. It could be any base. You have the variables, and then C will be this ring of coefficient to which you had all the variables x0, xn. Okay, so these are the notation. K is the base ring, ui's are indeterminate that present the coefficient of these general polynomials. Okay, and C is the polynomial ring over this ring of coefficient A. Okay, now what is elimination doing in this generic case? is to study this ideal I, in a sense, okay? And more we'll see just now to study saturation. So we'll give denote by I the ideal generated by the FIs, and by M the ideal of the variables x0, xn. B will be the quotient, okay? And the key degree will be this number delta, which is the sum of the degrees minus n plus 1, which is the, if you prefer, the sum of the degrees plus the A invariant of the ring C. In fact, that's how it counts, okay? But, or the sum of degrees minus 1. Okay, so what is the elimination ideal? Well, it's from a geometric point of view, just the idea. I defines a scheme in the projective space over spec A, and you want to look at its projection on spec A. Okay? And that's given by the elimination, which is obtained by taking the ideal I, saturating by the sufficient power of the ideal M, and intersecting back with A. Okay, so that's intersecting back with A is just doing the elimination, but what we will study more is this current ideal, I current M infinity, okay, in different degrees. Okay, so now, if you consider this graded map, which is the last map in causal, but that's just the map that corresponds to sending a tuple of n plus 1 tuple of polynomials to their to the combinations of the GIFI in some degree, so you put the right shift. Then for any integer mu, you have a matrix of that, say on the monomial basis on the two sides. Okay, and these are maps between 3A modules, and we call it phi nu. Okay, and the one important fact, I mean, there are many things, but is that if you take the ideal generated by the maximal minors of M nu, it has the same radical as A for all nu bigger than B. Okay, and this is, well, another way to say that is to say that the GCD of the maximal minor is the resultant, or thing like that. But this map, in fact, is very interesting by itself, and we'll somehow complete the picture of that in the talk. Okay, but let's continue first. So one goal will be to find smaller matrices with the same property. Okay, so this will give, both, formulas for resultants or things like that that are simpler, and also will give tools to do some computation that are interesting in practice. Okay, I will return a bit on that later. Okay, so let's go to Sylvester forms. Okay, so now if you, in the classical case, if you give a multi-index such that or if you prefer a monomial, if you put x to these exponents, it corresponds to monomial, with the sum of these indices smaller than the minimum degree. So if you prefer monomial smaller than minimal degree of the polynomials that are involved, then you can also decompose each Fi in this form. So the case we are, okay, the case of resultant that we'll see correspond to taking gamma equals 0. Okay? I mean, the case of, we'll see just after, it's the case of the Jacobian determinant somehow. Okay, but anyway, if you give any gamma, so verifying that, you can always decompose in that way. That's an easy thing to see. Just look at the exponents. Okay, you have minimal exponents in any of the variables in the forms. Okay, so this is, you can choose one such decomposition for each Fi. Okay, and then you, whoops, yeah, and then you define the Sylvester forms associated to this polynomial and this gamma as the determinant of these Fis. Okay, that's the construction. Sylvester, I think, did that himself for the case of two forms and two variables, and maybe slightly more. Okay, I don't remember exactly what did Sylvester. Now you check that the Sylvester form belongs to the saturation of the ideal, and it's of degree delta minus this m minus gamma. So these elements are pretty high degree. I mean, the degree are this sum of degrees delta, minus n minus 1 and minus gamma. Okay, so that's this degree delta minus gamma. Okay, and the important thing is that the Sylvester index gamma depend on the decomposition, but its class moduli do not. Okay, so it gives you an element in I stat mod I which is independent of the chosen decomposition. Okay, and we denote it by a small Sylv gamma. Okay, this class do not depend on the choices. Okay, and now in the classical case, one proves the following. This is, well, as I think not quoted due to Jussieu, is that for two multi-indices that are smaller than that and say the same, okay, then if you do the product of a monomial, okay, by the Sylvester form of which correspond to two different monomials that you find 0, and if you take the same, you find Sylv 0, 0, 0. Okay, and that's a very important property that shows, in fact, that the following theorem, the classical case, is that, I mean, for any integral nu, you have a duality. So you have a isomorphism between the homomorphism from B nu into A and I stat mod I in the complementary degree delta minus nu. Okay. So in particular, the saturation modulo the ideal is 0 in degree bigger than delta. Okay. So that's the classical result about elimination. You get also that in degree delta it's principal, and we'll see just about that. And in this pairing, the set of Sylvester forms, okay, is an A basis of gives an A basis of this, okay, and it corresponds to the monomial basis in C delta minus nu, okay. This is this thing here. So it's this duality transforms the Sylvester form into the monomials of complementary degree. Okay, so that's the duality here in the classical case. Okay. Now, I mean, to go to maybe a more familiar object, I mean, from the other formula, you can see that this Sylv 0, 0. If you multiply by the product of degrees, it's just the Jacobian determinant. Okay, but the Jacobian determinant has the inconvenience of not being giving the result in positive characteristic, or well, when this product of degrees is 0 in the ring. So it's better to use this other kind of characteristic-free Jacobian. Okay. Okay. So now, what this enables you to do, still in the classical case, is to look, in case of looking at this matrices only in degree bigger than nu, than delta, you look in degree that could be delta or up to delta minus the minimum degree of the variables, okay, and then you add to this map the map that sends gamma to Sylv gamma, okay. So you make a matrix, if you want, on monomial basis over A, where the first is this type of Sylvester matrix, a block matrix which corresponds to the different GIs, and you have a second block that corresponds to writing over the basis these Sylvester forms, okay, that you can explicitly compute as we have seen by decomposition and taking a determinant, okay. So you can fill up these matrices, and somehow this completes the picture, okay. So you have two blocks, the blocks mu, this always the last map of Kosul, and you have a second block, which are the coefficients of this Sylvester matrix, okay. And now, well, these are equal, okay. And now you can see that the ideal generated by the maximum minors of this has the same radical as the elimination, and still the GCD of maximum minors gives you the resultant. And moreover, if you specialize, that's also a property of the matrices mu for nu bigger than delta, is you specialize these matrices in a particular case, and you get a zero-dimensional scheme, so you get points then the failure of rank of the matrix is the number of points. So this is an additional property of these matrices, is that it enables you to compute, and you can compute, in fact, on these matrices to determine this zero-dimensional scheme. And you can go in smaller the degree than the usual degree, which is the sum of degrees minus 1 plus 1. Okay? So that's one goal of this matrices. Okay, so now I will move to the real subject of today, which is how you generalize that to a product of projective spaces. Okay. So now, when you're in the product of projective spaces, okay, so it will be so P1 cross P2 cross Pn1 cross Pnr, then you want to be able to do the same kind of things. So there is a theory of elimination there that was worked out in particular by Jussieu and some of his students. Okay, so you also have a resultant of this kind of theory, and this is also extended to the toric case by several people. I mean, Gelfand-Zelinsky, Kapranov, also Dickenstein, Catani, Sturmfeld. I mean, there were a lot of work on this extension of elimination theory to toric case. Okay, and so now, but I will stick to this product of projective spaces. So you will have, so you have these integers that are the dimension of the spaces, and will be the sum of the integers, so it's just the dimension of the space. Okay, xj, with this bold j will stand for tuple of variables. Okay, and now you consider multi-homogeneous polynomials of multi-degrees di's for different di's. Okay. And you take this generic form, so it's about the same, except that you have much more coefficient and sets of variables, and it's multi-homogeneous. Okay. And now you take also the universal ring of coefficients. Okay. And K is still any ring. You take I, the ideal generated by the Fi, so they're basically the same notations. B, now, the irrelevant ideal, what replaces the idea of variables, is that the natural ideal defining the empty set in this product of projective space, or if you want, is the ideal you should consider when you look at Koch strings of a product of projective space. The important thing is that the cohomology we support in B, in this ideal B, the local cohomology support in B will give you the sheaf cohomology on product of projective spaces. But also you have that if you look at the local cohomology supported in B, the cohomological dimension will tell you the dimension of the scheme if you're over a field. Else it will be the maximal dimension of fibers of a family of schemes. So this is like the maximal idea. It plays somehow the role of the idea of the variables in the case of one projective scheme. Okay? And so again, you have this delta, which is now about the same. It's the sum of degrees minus what is somehow the invariant also of this thing. It's the shift you need to do when you pass to the mechanical model in this multigraded setting. Okay? Okay, so this is pretty similar. But now, what happens is that you don't have a full duality like you have in the case of one projective space. This is not true. So what you have to consider is to look at some regions in the Z to the R where some cohomology are 0, and then you have some duality. So I will do that explicitly very soon in one example, and I will explain that in the case of two projective spaces, which is more simple. But the idea is that you have to look at the situation out of some regions of Z to the R, and these regions are defined by looking at the support of the cohomology in B of some causal factors of the causal complex taking on the F over your ring. So this is just a direct sum of copies of the ring with some shifts given by these sums that you have in the causal complex and these multi-degrees. So you have to look at these regions, and I will show just now what it gives in practice, okay, in one very simple case. But you have to consider this region in ZR that you have to, where also the behavior depends, even if you think to the case of one projective scheme, when you have n+1 polynomial in n variables, okay, if it defines the empty of a field, say, if it defines the empty scheme, it's a regular sequence, and you always have a resolution by causal, and the causal resolution is always the same. Well, it's no more the case in the case of product of projective spaces. Okay, for instance, you may have two ideals of n+1 polynomials of same degrees defining the empty set, but with different free resolution, with different Betty numbers, with different things. And you don't have this duality and all that. So it's more complicated. So, but still you have things interesting to see. So, but that's one example here, very simple example, but it's easier to see a simple example to be, understand what's going on. So this is for three forms of by degree 2, 2 in P1 cross P1, okay? And so you have these three regions. In red, you have the region gamma 0. In yellow, it's gamma 1. And in green, it's gamma 2. Okay? And so you see that, well, the theorem you see just after will tell you that you have duality if you're not in the union of the yellow and red regions. Okay? So, for instance, you have a duality between what happens in degree delta and in degree 0. Okay? Or by what happened here and what happened here, or by what happened here and by what happened here. So you have kind of duality, but it's not in all degrees, okay? So you have to consider these graded regions, okay? But what will be important is you have this degree delta, and you'll be able to say same kind of thing. If you're in degree delta, and you take off of delta something that is slightly smaller than the other degrees, for in this case it will be these 4 degrees, then you have a duality and you have a Sylvester forms and all that. Okay, so let's continue. Okay, so the first theorem, okay, is duality. So if you have n+1 generic multi-homogeneous polynomial of degree d0, dn, respectively, then if you're not in gamma 0 and gamma 1, you have seen just before, it was this red and yellow regions, okay, then there is a natural A modular isomorphism between this dual, like before, and the saturation modular in the mu, okay? So you have a duality, but only in some region. It cannot be everywhere anyway. I mean, it's not just not true, okay? And the second thing, well, first, a simple corollary. The simple corollary, this was already proved by the corollary by Jussieu, but by also in the Tori case by Catani, Dickenstein, and Schoenfeld, is that I sub mod I in degree delta is isomorphic to A, okay, to the polynomial ring, okay. And if you're not below delta and you're not in gamma 0 and gamma 1, then I sub mod I is 0. Okay, so maybe I can go back to the picture here. Okay, so it says here that if you're not in this, so first it says that inside the square here you have duality. Okay, and it says that if you're not in the red or yellow or smaller than delta, so you also have to exclude this block here where we have duality. Then I stat is equal to R. Okay. Okay. So that's the first result. Okay. Now we introduce Sylvester forms in this setting. Okay. So it's the same kind of thing. First, I should say it's not us that introduced Sylvester form. It was Jussieu and his students. No, I mean, Sylvester form is us, but the case of degree delta, it was Jussieu and his students, okay? And we generalize that to other exponents, okay? But this was done by Jussieu and two of his students in Morocco that came to Strasbourg later, okay? So what you do, okay, first we do it just for one, and this is Jussieu and his students. You decompose Fi as follows. I mean, so you start the same way with the first pack of variables, okay? Okay, but now, okay, so you decompose this way, and now the last one here, okay, you decompose it over the y's, okay? Okay, so you have this type of decomposition in the x's, and now the last guy, you decompose it over the y's, okay? So at the end, it gives this type of decomposition. Fi will be written over the xi's, and then for the first n-1, and then like x n-1, the last variable is y0 times g, x last variables times y1 times a second, and all that. So you take this kind of decomposition, okay? And then you define this twisted Jacobian, okay, as the determinant of all these guys. You multiply by the proper monomial here, okay? And the theorem, this is due to Jussieu and his students, says that this element is a generator of I-stat mod R in degree delta, which is known to be a free module of rank 1. But this points out the generator of this free module of rank 1, okay, in this multigraded set. I did it only for 2 packs of variables, but you can do that for any number, okay? So from now on, I mean, in this, when I describe, I take only 2 copies, because as you have indices everywhere, it's not so easy to, I mean, generalization is pretty natural when you know how to do 2, but I don't want to enter into too much technicalities, okay? So this is, again, very similar, okay? So you get a generator of this thing, okay? And this is a free model of rank 1, this was known, okay? And, okay, and again, I mean, multiple by a product of degrees of this is just obtained as a type of Jacobian determinant. This is also due to the other formula. So if you multiply the same monomial, and you take the derivatives with respect to the xi's, and then the second derivatives with respect to the last variable and the yi's, you will get a square matrix, and up to a constant, this gives you this generator in that degree, except that you have to be careful in positive characteristic, where the other works, and this only works with if no degree is divisible by p, the characteristic of the field, and the other one is really characteristic free. So this in the toric case is also could be extended. This is work of Catani, Dickenstein, and Schoenfels, or in characteristic 0, they work, I think. Okay. So now for multigraded Sylvester forms, we followed the same the same way as Jussieu introduced things. So you can always also decompose it. Now, if you have 2 indices, I will do for 2 that are smaller than the minimum of the degree DIs for each of them. Okay, then you can do the same type of decomposition. Okay, you decompose by putting higher power of this. This is possible due to these conditions here. Okay, and now you take this determinant, okay, and you define the Sylvester alpha beta of the forms, okay, to be equal to a proper power of the last of the x variables times this determinant. Well, you have to multiply by power, else you are not in the saturation. I mean, this is needed to be in the saturation. Okay. And again, you take the class of that in B, so modulo I, and then you look at this. This is of degree delta minus, well, the degree, the first degree, second degree, the degree of the monomial the bi-degree of the monomial you choose. Okay, And this is independent of the choice of the decomposition. Okay, so that's an important key thing to prove. It's not that difficult, but this is, say, maybe the more technical thing to check, to see, because in the classical case, so this was done by Jussieu and his students. For the case where you take alpha and beta equal to 0, and in the classical case, it's a classical lemma of Weber, because you have a complete intersection, which are the variables or powers of variables. And then you have this classical lemma that tells you that the determinant you obtain is independent of the choice of decomposition. This is no more the case here, because you don't decompose over a complete intersection at all. But nevertheless, this is still independent of the choice of decomposition. It's an important thing for the rest. Okay. And okay, now of course, the dimension of this, is the dimension of that. And of course, the main, so we want to obtain the main result, and the key to obtain this main result is somehow this term that tells you that the same phenomenon happens as in the classical case. So if you take two multi-indices, okay, so two multi-degrees, two monomials of the same multi-degrees, we should think at it like that, okay? Because, alpha 1, alpha r, beta 1, beta r have the modulus of alpha 1 is the same as beta 1, so it has the same degree, but the exponents are different. So if you take two monomials of same multi-degree, okay, then if you take the product of the monomial by the corresponding Sylvester forms, it is 0 if the monomial are not the same, and it is CF 0, 0, 0 otherwise. Okay, so the same claim holds. Okay, so this shows this is important to prove the main theorem that will come now. The fact that if you take for mu, so it extends, it was the case R equal 1 before, if you take integrals smaller than the minimum of the corresponding degree, okay, and you set mu equal mu1, mu r, so this is a tuple where each mu r is smaller than the smallest of the corresponding partial degree of the forms, then the set of these Sylvester forms yields a naive basis of the quotient isat modal, which is dual to the monomial basis here. And the duality is really between one monomial x1 to the alpha 1, x1 to the alpha correspond to Syl alpha 1 alpha. Okay, and the way we prove that is using the duality, because we know that there is a duality. Okay, so we know there is an isomorphism that respects the multiplication by the xi's somehow, and that's the way we show that this is a correspondence due to the term just above here. And then we deduce that indeed this Sylvester form forms the basis of the ISAT model. Okay. Okay, so now, well, I went a bit fast, but anyway, I still have two things to say. The first thing is that we found, to show an example of that, we found again the Dixon matrices for the resultant over P1 cross P1. Oops, here. So what Dixon did in, more than a century ago was to, for three, well, there was a lot of people working on the elimination theory and trying to have formulas for different type of problems. Okay, so for the resultant, of course, but also for resultant in things like over P1 cross P1. So you have three forms over P1 cross P1, and you want to know there's a universal polynomial that tells you if ever they have a common zero or not. Okay, and this is the Dixon resultant, say. And now Dixon showed three formulas to compute this that are given by determinants of size 6 times the product of degrees, 4 times the product of degrees, and 2 times the product of degrees. And now using this the equivalent of what we explained in the what I just explained in the single projective case. When you can extend it, of course, to the multi-projective case. I didn't do a slide of that, but you do exactly the same. You have your matrix of the GIs, and you add to this, this Sylvester forms. Okay, so you have a two-block matrix done exactly the same way. Okay, and in this very, very small case, you have, you see, the classical construction that always work with mu, this matrix that only in this region here, okay, they work here. But now with this hybrid thing, you also are able to have these new matrices here, okay, that gives you another way to attack this, okay, where you complete these matrices, they give you smaller matrices, and on these red lines here, okay, you have that you obtain things that are just square matrices, and the determinant of the square matrices will be the Dixon resultant, okay. So the Dixon formulas, the one of degree 6 dE where this here, this extremity is here, and the one of degree 4 dE with this extremity here. And you see that this gives you several determinant of formula all along these lines here, okay? And the most compact you have is this here with this approach, okay? But you also have in all of these, some formulas, but then if you're not on this red, the two part of red lines, this is not given as a determinant. It will be the quotient of a determinant by another determinant. Okay, so if you go in higher degrees, so it's not as nice formulas. Okay, so I just made a slide to say a few words about specialization, because in fact it's something that is very interesting in the applications. Okay, so now you have this very generic case where you can describe all what happens somehow, at least in principle, because if you want to compute essentially any of these determinants, you will never end. These are huge determinants, okay, and with indeterminate variables, thousands or billions of variables, whatever. So what you're interested in application is to know for a special case what happens, okay, and this helps to compute, okay. So now, if you consider that you have such a system in a product of projective space, or one projective space, okay, and you give n+1 polynomials, where n is the dimension of this product of projective spaces of some degrees, okay, so you see them as specialization of the other one. But of course, these huge matrices, okay, you can specialize them also. Or in fact, you can also take a decomposition for your specific polynomials, okay? And well, even if they don't live that way, the decomposition, it doesn't really matter. But anyway, you can take these matrices from the generic case and specialize them, okay? And now the theorem is that if your polynomials define a zero-dimensional scheme in the product of projective spaces of some degree kappa, then for these degrees that we have looked at, so in degree that is in delta minus this minimum plus n to the r, but of course, usually the most interesting degree is the smallest. So we take delta minus this minimums, okay? Then the co-rank of this matrix, so the usual causal matrix complemented by this Sylvester forms of this degree, as the proper rank. So its co-rank is equal to what is expected. So that's the number of common zeros. And moreover, somehow these matrices represent these. Okay, so the failure of rank, you have a failure of rank, but for instance, you can also use in practice the matrices to find the coordinates of the zeros and things like that. Okay, so this is very commonly used when you take the degree, the critical degree, which will be, for instance, in the product of two projective spaces, this will be the two critical degrees, this one and this one, okay? The two smallest ones that are not here. But now you're able to use this degree here, okay, where you have much more matrices, okay, but you have to fill up with this 2 blocks, like usual, of Sylvester matrix, or 3 blocks of Sylvester matrix, a small one, and the last will be filled up with this coefficient of Sylvester forms, okay? And then you can use these matrices, which are much more, to be able to work on this zero-dimensional scheme, determine the degree and all that, and to, well, I don't have time to, but it's important in practice to have a representation. What is used, for instance, in geometric modeling often is you want to know if you're on the surface, and to know if you're on the surface, it's pretty easy to specialize and see if the rank of a matrix fails or things like that. So it's really this kind of obtaining this kind of matrices is useful in practice. Okay, so I think I'll stop here, quite in advance, in fact. I think I went too fast, but anyway. Thank you. Oops. Jürgen, your microphone is off.
Now it's on.
It's okay.
Okay, I want to thank to Marc for his interesting lecture, and I invite the audience to ask questions about it. For example, I was not attentive enough. Did you have any assumption about the characteristic?
No, not even about the ring. Any commutative ring is okay.
Ah, really? Uh-huh.
Yeah.
So,
no.
And yeah. When you consider the modular saturation I sub modulo I, right?
Yes. Yeah.
You get this saturation by taking a high enough power of the ideal, a maximal ideal.
Yes. Yes.
Can you estimate these numbers, the smallest number, to reach the saturation?
Yes. At least in the classical case, yeah. It's sufficient to saturate, but I think it's again this delta is sufficient, but maybe smaller than that. I don't know.
Could be smaller, right? Yeah, could be smaller, of course. Yeah.
I don't remember the exact answer, but yes, you can say what. Yeah. You have an explicit form how, for instance, to write a power times the resultant in the ideal. This is really explicit. I mean, you can, in terms of partial derivative of the resultant or thing like that, and you have control on that. So, I mean, you have very explicit thing about that. I mean, if you look in Jussieu's, for instance, Jussieu's first paper, I mean, le formalisme du résultant, you would have things like that, I guess.
Are there any other questions?
Yeah, Marc, I have a question.
Yeah.
So in one of the slides, you mentioned that the multigraded Sylvester forms give you a basis of I saturation over I in certain degrees.
Yes, yeah.
Yeah, so suppose this ideal I is bigraded, just take bigraded situation.
Yes, yeah.
And then replace I by powers of I.
Yeah.
Then can we predict the behavior of this dimension as the powers are growing? So we get a bivariate Hilbert function.
Yeah, I know. But
you have explicit basis. Maybe the number is known, the rank is known.
I don't know. I didn't look at that. It could be because you. It could be that one can have control of that, but I don't know because usually when you look at power, you want to look at powers. you may have to look also at, say, this is like looking at the torsion of the the torsion of the H0 of the causal complex, thing like that. And usually you have to look at also the B torsion of the higher causal homology. And this I don't know. I didn't look at that. You know, I mean, usually, at least the process I know you use this approximation complexes or thing like that to be able to say things on powers or symmetric powers. But from symmetric you pass to powers. I mean, from the causal homology or from this thing. But this here, you only use, I mean, the zeroth causal homology, really the quotient by I. So I don't know. Maybe one can say things, but I don't look at that. So
okay.
I won't guess like that.
Okay. Thank you. Thank you.
Okay. Any other questions? Okay. Then there are no further questions.
Okay.
Then I would like to thank again Marc for this interesting lecture and close the session for today.
Okay.
Okay.
Bye.
So, bye all of you.
Okay.
Bye.
Bye. Thank you.
Bye.
Thank you.